Today, from walk-in LAN parties to diskless data infrastructure pioneer, this is Confluent Developer.
And as we were getting ready to kind of like migrate our first product, we realized it just like kind of didn't work. Someone's day is going to be ruined every day at that level of nines. When it was not working and we were grinding on it, trying to make it work, I was like, man, I might have to eat some crow. Like, this is not working.
Hey there, everybody. I'm Tim Berglund, and welcome to Confluent Developer, the podcast where we explore the journeys of software developers tackling really hard problems. In this episode, I'm interviewing Richie Artoul, who's famous for being the founder of the pioneering diskless Kafka implementation WarpStream. We talk about his first job at a gaming cafe and some really pivotal work he did at Datadog, redesigning their log storage engine and indexing system. Richie tells a great story. I always really enjoy talking to him, so let's get to it. Welcome to another episode of the Confluent Developer Podcast. I am your host today, Tim Berglund, and I'm joined by Richie Artoul. Richie, welcome to the show.
Hey, Tim. Thanks for having me on.
You got it. What do you do right now? What's your current job, current title? What are you all about?
My current job is Director of Engineering for WarpStream at Confluent. So I lead essentially what is like the WarpStream group at Confluent. So we're like a product line. So we have kind of like our own software and own product.
Yeah. And it is a fascinating one. Maybe we'll talk about it today. Maybe we won't. What was, before you did that, long before that, your first job? What was your first job ever?
And you want like my real first job, right?
Real first job. Like, I don't want your first, interned at Google writing. That's like your actual.
Okay, cool.
Yeah.
Yeah, so I mean, I actually didn't study like computer science in college or whatever. So my first job out of college also wasn't tech, but
Okay.
my first real job was working at a place called Howie's Game Shack, which I think I was 16, and it was like I forget what they're called, like one of those places you can go, like an internet cafe.
Yeah.
But it was all games, so they had like 50 Xboxes and like 100 PCs, and people would go and play like Dota, like on Warcraft. I don't know if you ever heard of that game. And Counter-Strike and World of Warcraft there. And I think this is when like the iPhone had just come out, and I like really wanted one because I just wanted to have access to the internet all the time.
Sure.
I was a nerd.
Right.
And I was like, okay, so I need a job. So I got a summer job there. And I think I made just about enough money to pay for an iPhone. So
That is amazing. So it was like a retail LAN party was the business.
yes,
You walked
yeah,
in.
that's exactly what it is.
Oh,
Yeah, it was an interesting group of people.
That is, yes. I mean, look, it's kind of our people.
Yeah,
we
exactly.
we can say that. And yes,
No,
it is a
I've-
very interesting group of people.
Yeah. Well, especially just because it was a lot of like, high school kids and college kids, and I was 16, so it was fun. It was a good first job.
That is an amazing first job. I love that. And I want to go there. I mean, I don't know if that's even a business that exists anymore, but it just sounds like a fun place to hang out.
Yeah.
Well, you mentioned that you weren't a computer science major. This isn't scripted, but what was your major? What'd you do in college?
I studied biochemistry and pharmacology. My dad's a doctor. I was told to be a doctor from a young age. That was the plan. And then in college, I kind of realized like I didn't like hospitals, so I was like, I probably shouldn't be a doctor. But I was kind of like top of my class, pre-med, that sort of thing. And then just decided to not take the MCAT. So I just ended up working some kind of weird office job doing like, editing Word documents type of thing after college.
Finding your way.
Yeah. And then obviously hated that. I think like about 10 months into that job, I just was kind of like losing my mind and just kind of like rage quit and went to a coding boot camp. And so that's kind of how I got into tech.
I love it.
Yeah.
I did not know that part of your story.
Yeah.
That is fantastic.
Yeah.
And I think we're all kind of glad you did.
Thanks.
So the big question of the show: what's the most interesting problem you've ever solved? I mean, I got to tell you, I'm expecting you to say WarpStream, but I don't. Maybe you're not gonna. So you get to surprise me. What is it?
Yeah, I think. Yeah, I mean, it's lots of stuff. Obviously, I could talk about related to WarpStream.
Hey, we might have you on the show again, just so you know. So
Yeah, exactly.
you do it.
But one of the things I thought might be kind of interesting was it was actually my job before WarpStream, which I was working at Datadog, and we basically Datadog ingests and stores all your logs and events and time series data. And I was part of the team that was building the new storage system, basically to replace the existing one, for a lot of that data. And building that system was like super fun, and we did a bunch of cool stuff. But like the part that was actually like really hard and kind of a grind was like, okay, how do we get this actually out into production now for like 100% of products and customers? Datadog has like tens of thousands of customers and dozens of products that are all powered by like one database. And you got to imagine.
Let me actually, I want to ask you about that. Like, what was wrong with the world of Datadog that they wanted to build the new system? What did it? And I'll take like the business perspective. I'll take the developer perspective, hands-on. Like, what was it?
Yeah. So the business perspective is, I think, super easy. One, it was like just like insanely expensive what they were doing.
There you go.
Which is for all the same reasons, really. That I'll slip WarpStream in, which is that running kind of open source Kafka yourself can be really expensive. Networking, storage, auto scaling, all that type of stuff. So a lot of the same impetus for WarpStream, but this was before WarpStream, but similar problems. And so that was kind of like the cost was an obvious one, but actually a lot of it too was like there was a lot of stuff that customers wanted in terms of like features that we just couldn't deliver with the existing system. So like one of those, I don't know how obvious this will be to someone who's not like a Datadog user, but like if you imagine a logging UI, right, like there's a little bar at the top, and you're like you filter on things, and in the older versions of Datadog, you used to have to say beforehand, these are fields that are interesting to me, and I would like to be able to filter on.
Before ingest.
Correct. Yeah.
Oh, okay, good. As long as you know everything ahead of time, it's fine.
Yeah, which is great. So it's like you'd be in an incident, and you're like, oh, I need to filter on this field, and we're like, no, you didn't tell us beforehand. And then you could start indexing it in the moment, but it would only apply to new data coming in, several minutes later, not to anything in the past. So that's obviously extremely frustrating.
Yeah.
But if you think about it, without going into too many details into how the old system works, if you imagine like a traditional search system, usually there's like an index, like a schema for the index, right? You're like, well, these are the fields that are important, but like every customer's logs look different, so that doesn't really work for like an observability use case where the customer doesn't like give you the schema. So that was just like one example of a feature that we couldn't really implement in the old system that the new one could. And the other was just query performance, really. Like, the old system worked fine if you just need to query a couple hours of data, but what happened is someone wants to query like 3 months of data.
Oh.
And they're a relatively low volume customer, so they were on like one shard over here, and a shard is like physically tied to like a machine with a fixed number of cores, and so if we only had your data on this machine, but you wanted to run some massive query, there was no way for us to parallelize it beyond what we had decided 3 months ago how many machines yet you deserved, basically.
Gotcha.
So kind of that sort of thing. So
which is a very much first generation distributed data architecture kind of
exactly.
choice. That's common.
Yeah. So those are the kind of the reasons that we were building something new. We wanted something cheaper, something more cloud native, easier to scale, easier to manage, but also something that would allow us to kind of build some of these new features, and something where like, hey, even if you're a tiny customer, if I want to throw 1,000 computers at your query for a second, I can.
Okay, so thank you. That's the what was wrong. That makes a lot of sense. And you were starting to dive into like a particular storage problem. Keep going. Now, a quick word from our sponsor. Confluent Developer, the podcast, is brought to you by Confluent Developer, the website, which has everything you need as a developer of data streaming systems. And it's completely free. We've got curriculum, hands-on exercises, executable tutorials, the online data streaming engineer certification, also free, a way to find a meetup near you, those are free. Everything is there. I really want you to be successful in your journey as a data streaming engineer, and this is the site that has what you need. Check it out at developer.confluent.io. That's developer.confluent.io. Now back to the show.
Oh yeah, it was just the general problem, I would say, of like getting out to production, because about a year in, we were like, okay, we built a pretty good system. Like, it's not perfect, but it's decent. Like, it can do some pretty cool stuff. But like the reality of like hot swapping the database for like 30,000 customers and 13 distinct products with different features, different query patterns, like the reality of doing that without breaking everything was hard.
Yeah.
So there were kind of like a number, and what we ended up doing was we just tackled it product by product. So we picked like the simplest product we could, and we'd be like, okay, like let's just focus on this one. And because you got to imagine too, if you mess up, like let's say filtering, because Datadog query language is super weird, because like, so imagine you're like duration larger than 200 is like a filter you put into your logs, right?
Okay.
Well, some customers may be emitting the duration field as a string, and some other people may be emitting it as a float, and someone else might be implementing it as an integer, and some customers may be mixing and matching those from like the same service. And so the query semantics get funky, and if you mess up the query semantics, someone might get paged in the middle of the night for something they shouldn't have been,
Right.
or worse.
Or not.
Yeah, the opposite. Yeah, exactly. So you have to be very careful and do all this kind of query shadowing stuff. And I remember one of the things that like really killed me was, we were kind of getting ready to migrate our first project, and this requirement that I like had been vaguely familiar with but didn't really understand the real implications of, which is that in Datadog the storage system basically ensures that you only ingest each piece of data once. Like every log, everything that we ingest, like it's like a JSON record, has an ID.
Okay.
And the storage system is capable of making sure that it only ingests it one time.
Okay.
Which is also super important, because like you can imagine a lot of people have monitors that are like, if this happens more than 3 times in 5 minutes, page me. And it's like, well, if some intermediary service in Datadog's processing pipeline restarts and replays a couple of messages, and then those end up in storage twice instead of once, that will like ruin someone's entire day, basically, right?
Okay.
And so it's extremely important that like if you send us something once, we store it once, and it shows up once in the query. And that, if you imagine kind of like a database that's on SSDs and sharded, it's relatively straightforward to implement that feature. It's not easy, but like you can do it. You're like, okay, well this record goes to this node on this shard, and that thing can kind of check because it's it's a KV store or whatever it is. But when you've built like a kind of columnar store on top of object storage, like, hey, does this ID already exist in the system, becomes like a very hard problem to answer. And so we built a thing to do this, and as we were getting ready to kind of like migrate our first product, we realized it just like kind of didn't work. Like it worked 99.9% of the time, but that wasn't like good enough.
There were some
like,
edge cases that were there. Yeah.
Yeah, I think at one point we had it up to like, we measured it. We're like, okay, we're at like 5 or 6 nines of deduplication, which like seems like a lot, but is still like not enough.
Sure. When you're looking at volumes like you're ingesting, there's still a significant number of duplicates.
Yeah, like someone's day is going to be ruined every day if we at that level of nines. And so it was like me and another engineer. We were basically like, all of the work we did building this system is for nothing until we solve this like to like 29s or whatever, basically. And so it took us about 3 months of basically just grinding on that feature to get it working. Yeah.
How did you find that? You started by writing something that I'm going to guess you believed did deduplication.
Yeah.
And then you find out you're wrong. How did you find out you were wrong at the beginning of that 3 months?
Yeah, I'm trying to remember how we noticed at first. Well, in the beginning, it didn't work well enough that like people would like notice and complain. Like our internal, like the Datadog things, like not before we migrated customers, we'd migrate Datadog internal products.
Okay.
And there were like parts of the product that would just like break basically if this happened.
Okay.
And then when we realized the problem was more complicated than we had kind of anticipated, I think what we ended up doing was writing a bunch of tooling to detect it. So we had a couple of tricks. One, we could detect, like for certain types of queries, it was easy to detect that like, hey, there's 2 duplicate events
Right.
in this result. So we did that. And then we had this compaction system that was constantly merging data in the background. And so we, and what that would, that system was designed to bring similar data closer together, basically, to make queries faster. And so we added a bunch of code in there too to detect, essentially like, hey, while you're bringing similar data close together, kind of look around yourself to see, hey, are there duplicate, kind of do like a sliding window scan during the compaction to see if you have duplicate events in there.
Okay.
And I think we then built some other tools that would essentially go and download a bunch of files, analyze them, look for duplicate events, and then emit logs and stuff. So we built a bunch of tooling basically to kind of passively scan in the background to see if we messed anything up. And then we would go and manually cause this to happen to see if our tooling detected it.
Right.
So we just had to build a bunch of tooling. And we probably should have done that. This probably should have been the first thing we did. I think we just were kind of like in a rush and didn't build enough tooling in the beginning.
Yeah, and
so
you usually believe you're doing it right. You think you have a solution that works until you bump up against reality.
Yeah, exactly.
What was that tooling the final answer that these tools run and detect duplicates, or did that cause then you to go back into the deduplicate? I mean, did you effectively solve deduplication on the input?
The tooling gave us like a benchmark, basically like, okay, until these go away, like we're not done. And even then we may still not be done, but we'll be like much closer to done. 'Cause, I mean, they would like, once we started building smarter tooling, there were tons of operations we could do and we'd be like, oh shit, it fired because, we scaled this up, scaled that down, killed this node at the wrong time, or we'd inject faults and see that was happening. So I would say that's actually when the work began, is when we started having those tools. And then it was like literally like, okay, well, and part of what made this hard too is it wasn't just localized to our system. Like our system, in order for our thing to function correctly, it depended on services sitting upstream of us. Because like, essentially what the system did was like, for example, if 2 duplicate events were ever sent to, we had these things called shards, and a shard was essentially a group of Kafka partitions. So if anyone ever sent, you sent an event with this ID to this shard, and then later you sent a duplicate event to another shard, our deduplication system just did not work. So all of our upstream things also had to be functioning as well, which ended up being cool because eventually we got our thing working perfectly, and like a couple months later it fired, and it turned out we had caught a bug in something upstream of us, basically. So our thing, it was our scanners, because they essentially just ran passively in production, were able to catch issues that arose even outside of our own system, which was cool. But that's what made the problem so hard in the beginning, is like there's so many moving pieces, and it's not working, but where did it go wrong? That's very hard, right? So I think we someone ended up writing a TLA verification of the protocol we were trying to implement, just to make sure, like, is there just like a logical fallacy in the algorithm we're implementing?
And if anybody listening doesn't know TLA, tell us briefly about that.
Man, I'm not the right person to explain these things, but it's a don't quote me on my explanation, but it's essentially under the category of formal methods, and what it does is allow you to express distributed systems and concurrent algorithms in like a formal language, and then essentially run it through a simulator, and the simulator will essentially like explore the solution space and tell you if any of the like invariants you said must always be true are ever violated.
Right. And it's pretty common. I'm blanking on what TLA stands for. We'll look it up. We'll put it in the show notes.
Yeah.
But I think it's common experience when you've built your system. You're like, hey, this works. Let's do TLA. Oh, it doesn't work. It's usually humbling, right?
Yeah, and the thing that's really cool about TLA Plus, I haven't done it a ton. I've done it like 2 or 3 times in my career, but it's like, people say like writing, like you don't understand something, or you haven't thought something through until you've written it down, because writing is thinking.
Yeah.
I think TLA Plus takes that to like the logical extreme.
There you go.
For computer algorithms, it's like you don't really understand a distributed algorithm until you've implemented it in TLA Plus, and then you really know. Like, it's almost like I often will find bugs not because TLA plus like the simulator found it for me. It's because while in the process of trying to translate my thought into a TLA plus spec, you're just like, oh, that's just like wrong. Like you'll see
Yep.
it while you're
Yep.
trying to implement it.
The discipline of translating it into the formal
Yeah,
specification.
forces you to grind
Yep.
through.
Yep. Just like writing or even explaining
Yeah.
verbally. If you can't do that in a simple way, I totally agree. That's without having used TLA to verify any distributed algorithms I've written. The whole concept that makes sense. You were you had deduplication solved, and you said you had caught a bug. It had been running okay for a few months, and your monitors caught a bug in some other upstream service, which is really cool. What was this could rabbit hole, and we don't need to do that. So, kind of in brief, you described the problem at the beginning. When you write something to storage, you need to make sure you're only writing it once. And there are two things, I suppose, two categories of things that could be hard about that. One is the definition of something, like the identity of the thing.
Yeah.
I'm going to guess that was solved. There were some unique IDs somewhere. That was all okay. And the hard part is race conditions on the writing or the reading. What was the storage? Was it a blob store? Was it disks? Was it something
Yeah.
you guys had built?
So this was another thing that was interesting, which was like we decided, okay, so we built this completely stateless ingestion thing, like, our compaction service stateless, our ingestion service was stateless, our query services were stateless.
Seeing
You
a
go and
trend
delete,
in your
nuke, or whatever. Yeah.
in your
Yeah,
architectural preferences here.
yeah. I like to sleep at night,
Yeah.
And so we built this completely stateless system, and you could go delete anything at any time, and you would never lose any data. And then when we were designing this deduplication system, we were like, we can make this work with no disks too, and no state and any of this stuff. And I got a lot, not just me, we got a lot of flack for that because I think there were some other people at the company that wanted us to just like essentially stick RocksDB on some nodes and do the deduplication there.
As one does.
And have it be pretty stateful. And that would have made the problem maybe not very easy, but let's say much easier. But we really didn't want to do that because we were like, man, we literally built this whole thing and now we're at the final step and we really don't want to just shove disks in here at the very last moment. And then when it was not working and we were grinding on it, trying to make it work, I was like, man, I might have to eat some crow. Like, this is not working. It should be able to work, but it's not working. And what was interesting is that we actually were using the system we built to store. If you think about it, like the deduplication thing essentially boiled down to, it was essentially another database that needed to track IDs and be able to commit atomically with the other data file ingestion.
Yeah.
And we were like, well, if we start creating files that just have IDs, we can organize them the way we want so we can query them quickly. But then we'll have a lot of files and we'll need to compact them. And then when the files get old, we'll need to expire them. And we're like, we're going to have to rebuild half of this database. And so what we ended up doing was storing them in the system itself, that they were also serving as the deduplication layer. So they were essentially special tables in Husky.
Okay.
And they would go through their own compaction, which sounds like meta and weird and like it wouldn't work, but it did end up working and saving us a lot of work. Because then it's like, well, you get compaction for free and you get data expiry for free and you get a file format for free. So that's how we did it. And the IDs they were very specifically shaped. Like they had time in them and some like tenant information and whatever, which allowed us to compress them like crazy in memory. Because what we didn't end up doing any disk, but we did end up doing is like having essentially a hot set that was in memory that we could verify against very quickly.
Okay.
And we would essentially page them in and out of memory very quickly. Sorry, I feel like I forgot what the original question you were asking was.
What was hard about basically I think the most recent question was, were there disks or not? And you're saying ultimately no?
No, there were no. We did manage to make it work with no disks at all. Built on top of the system that it was supposed to be essentially deduplicating for, which ended up being
clever.
And it was nice because it ended up being a really simple once we ironed out the kinks, it was very stable, and you just kind of like you could add new nodes, and they could start processing data, and they would load whatever they needed for deduplication into memory. And if they died, work would get transferred over, and you didn't really have to think about it too much. But there was definitely a window where I was like, this may not work. Like maybe we built more than we can chew.
Yeah.
And we just kind of eventually we ground through it. But I was definitely worried for. That was probably the most in my career of like this may never work type of thing, because we were working, it was like 3 months of like probably 6 to 7 days a week, 10 to 12 hour days, just trying to get this thing because it was blocking everything. You know what I mean? Like until like this graph we had essentially went to zero, you couldn't get any value from any of the system we built. Yeah.
Right. Of course, that makes sense. Yeah. And that value after you shipped it, beforehand. You had to define indexes in advance. It was really expensive. It was slow. Those things got better. I mean, is that?
Yeah, way better. So like, product owners could be like, I would basically tell them the difference between 1 day of data retention and 2 weeks of data retention is almost nothing. And so products could have higher retention by default. You didn't have to pre-index your field. So if you're in an incident, you saw something weird, you needed to go look at some historical data during the incident, you just could. And that started working. We were able to add more powerful autocomplete. And obviously the company saved just, a ton of money not running this super expensive, kind of SSD-based system for what is essentially the lowest value per byte data on the planet, right? Which is like, random metrics and logs coming out of your software, right?
Yep, the exhaust. And what year was this?
That's a good question. What year? It was. How old is WarpStream? WarpStream's like 2.5 years old. So I guess this would have been like 5 years ago.
Okay.
Like that. So like 2020 or something.
And yeah, like WarpStream's. I guess that's really the thing. WarpStream's 2.5. And now this is late 2025 when we're recording this. Diskless whatever is the cool thing. If there's a kind of data infrastructure, someone is working. And probably 2 or 3 someones are working on a diskless version of it. Yeah. Search various kinds of databases. Certainly distributed logs. That wasn't true then. That was you try to do this all diskless. That was a much riskier choice for you and direction for you. And it's funny. Your story kind of pivots on that all is lost moment of, oh crap, maybe I did the wrong thing and we have to go back to doing this the lame way. And you didn't, you pulled it out. But that's, these days, like if that's happening in 2025, early 2026, oh, you want to do something diskless, big deal. Everybody does that. It's hard, but it's popular. It just wasn't then. And I'm pointing out that was an admirable and slightly revolutionary approach.
Well, that was, I think, less, I don't know what word to use, unhinged maybe, than when WarpStream actually, because like I think at that time, we were kind of following in the footsteps of like the Snowflake paper was published. People knew that building analytical databases and columnar stores on top of object storage was possible. People thought maybe, it'll have to be like a cold store, because that's how the project started. People were like, oh, you're going to build like the cold tier or some special, really slow version of the logs product that's cheaper or whatever. And then like 6 months into the project, like one of our engineering leaders was like, no, you need to make this work for every product and to get rid of the old system to power all of the real-time data as well. And I was like, man, that's going to be hard.
Yeah.
Because there's, we'd already set some latency expectations with the old product. And I think WarpStream was even more extreme. That like people, the way people used to describe it was a aggressive architectural decision or whatever.
I've probably used those words myself.
Yeah, because you think of it being as a much more, you can kind of imagine, okay, like if a query takes a second to run to answer a human, that seems more reasonable than like a computer waiting 500 milliseconds to make sure something is durable or whatever.
Right.
But I don't know. I think if you're working on stuff that's like really hard or bleeding edge, at some point you will find yourself questioning like, at some point you'll have a come to Jesus moment where you're like, I don't know if this is ever going to work.
Exactly. Am I the stupid one here?
Yeah. Like I've had that moment in pretty much every major project I've ever worked on.
Yeah.
Just because it's like if you're doing something ambitious, you will eventually reach a point where you're like, I don't know if it's gonna work. Like the napkin math said it would, but I'm not getting the results yet.
As I like to say, it's hard to make things, and if you're not struggling a little bit while you're making them, you're maybe not making something that is all that interesting.
Yeah, I agree with that.
My guest today has been Richie Artoul. Richie, thanks so much for being a part of the Confluent Developer podcast.
Thanks for having me, Tim.